Hello everybody, my name is Michael. Thanks so much for joining me and welcome back to the channel. Before this video begins, I just want to preface that I am reading from the third edition of Introductions to Algorithms by CLRS. At the time of reading, I did not realize there was a fourth edition. So chapter 1, unfortunately, is from the third edition, but it is good news that there is very little differences between the third and fourth edition in chapter 1. And moving forward from chapter 2 on, we are reading out of the fourth edition. So thanks so much for joining me, guys, and enjoy the video. Introduction to Algorithms, third edition by Corman and some other people involved at MIT. I'm gonna do my best to read here, so sorry if I mess up a couple times. I ain't no pro. Chapter 1, the role of algorithms in computing. What are algorithms? Why is the study of algorithms worthwhile? What is the role of algorithms relative to other technologies used in computers? In this chapter, we will answer these questions. 1.1, algorithms. Informally, an algorithm is any well-defined computational procedure that takes some value or set of values as input and produces some value or set of values as output. An algorithm is thus a sequence of computational steps that transform the input into the output. We can also view an algorithm as a tool for solving a well-specified computational problem. The statement of the problem specifies in general terms the desired input/output relationship. The algorithm describes a specific computational procedure for achieving that input-output relationship. For example, we might need to sort a sequence of numbers into non-decreasing order or increasing order. This problem arises frequently in practice and provides fertile ground for introducing many standard design techniques and analysis tools. Here's how we formally define the sorting problem. Input is a sequence of n numbers, a1, a2, all the way up to some number of a sub n. And output is a permutation or reordering of the set of numbers, sequence of n numbers, where you have a prime, a sub 1, a prime sub 2, all the way to a prime sub n, where I'm guessing that these are just, a prime is the reordering of these sequence, right? Whereas a prime is less than a prime sub 1 is less than a prime sub 2, which is less than, all the way up to a sub prime n. Yeah. For example, given this input sequence, 31, 41, 59, 26, 41, and 58, a sorting algorithm returns an output sequence of them in sorted order. Such an input sequence is called an instance of the sorting problem. Because many programs use it as an intermediate step, sorting is a fundamental operation in computer science. As a result, we have a large number of good sorting algorithms at our disposal. Which algorithm is best for a given application depends on, among other factors, the number of items to be sorted, the extent to which the items are already somewhat sorted, possible restrictions on the item values, the architecture of the computer, and the kind of storage devices to be used, main, memory, disks, or even tapes. An algorithm is said to be correct if, for every input instance, it halts the correct output. We say that a correct algorithm solves the given computational problem. An incorrect algorithm might not halt at all on some input instances, or it might halt with an incorrect answer. Contrary to what you might expect, incorrect algorithms can sometimes be useful. If we can control their error rate, we shall see an example of an algorithm with a controllable error rate in Chapter 31 when we study algorithms for finding large prime numbers. Ordinarily, however, we shall be concerned only with correct algorithms. An algorithm can be specified in English as a computer program or even as a hardware design. The only requirement is that the specification must provide a precise description of the computational procedure to be followed. What kinds of problems are solved by algorithms? Sorting is by no means the only computational problem for which algorithms have been developed. You probably suspected as much when you saw the size of the book. Our practical applications for algorithms are ubiquitous and include the following examples. The Human Genome Project has made great progress toward the goal of identifying all the 100,000 genes in the human DNA, determining the sequences of the 3 billion chemical base pairs that make up the human DNA, storing this information in databases, and developing tools for data analysis. Each of these steps requires sophisticated algorithms, although solutions to the various problems involved are beyond the scope of this book. Many methods to solve these biological problems use ideas from several of the chapters in this book, thereby enabling scientists to accomplish tasks while using resources efficiently. The savings are in time, both human and machine, and in money, as more information can be extracted from laboratory techniques. The internet enables people all around the world to quickly access and retrieve large amounts of information. With the aid of clever algorithms, sites on the internet are able to manage and manipulate this large volume of data. Example of problems that make essential use of algorithms include finding good routes which the data will travel, Techniques for solving such problems appear in Chapter 24, and using a search engine to quickly find pages on which particular information resides. Related techniques are in Chapter 11 and 32. Electronic commerce, e-commerce, enables goods and services to be negotiated and exchanged electronically, and it depends on the privacy of personal information as a credit card numbers, passwords, and bank statements. The core technologies used in electronic commerce include public key cryptography and digital signatures, covered in Chapter 31, which are based on numerical algorithms and number theory. Manufacturing and other commercial enterprises often need to allocate scarce resources in the most beneficial way. An oil company may wish to know where to place its wells in order to maximize its expected profit. A political candidate may want to determine where to spend money buying campaign advertising in order to maximize the chances of winning an election. An airline may wish to assign crews to flights in the least expensive way possible, making sure that each flight is covered and that the government regulations regarding crew scheduling are met. An internet service provider may wish to determine where to place additional resources in order to serve its customers more effectively. All of these are examples of problems that can be solved using linear programming, which we shall study in Chapter 29. Although some of the details of these examples are beyond the scope of this book, we do give underlying techniques that apply to these problems and problem areas. Also show how to solve many specific problems, including the following. We are given a roadmap on which the distance between each pair of adjacent intersections is marked, and we wish to determine the shortest route from one intersection to another. The number of possible routes can be huge, even if we disallow routes that cross over themselves. However, how do we choose which of all possible routes is the shortest? Here we model the roadmap, which is itself a model of actual roads, as a graph, which we will meet in Part 6 and Appendix B, and we wish to find the shortest path from one vertex to another in the graph. We shall see how to solve this problem efficiently on Chapter 24. Don't get too caught up in kind of these examples here, as they're kind of just kind of preludes, precursors, and kind of foreshadowing to what's coming in the future chapters. This is kind of like an introduction in the roles that algorithms can play into solving these kinds of problems to kind of pique your interests. And so, yeah, don't really get too caught up in these examples right now, as it kind of can be kind of daunting, for sure. We are given two ordered sequences of symbols. X equals to a sequence of x1, x2, all the way up to xm, and y of the same sequence all the way to y sub n. And we wish to find the longest common subsequence of x and y. A subsequence of x is just x with some, or possibly all or none of its elements removed, right? It's just a subsequence of a sequence, is a chunk out of it. For example, one subsequence of A, B, C, D, E, F, G would be B, C, E, G. Interesting. B, C, E, G, so that you can skip the D? Pause. The length of the longest common subsequence of x and y gives one measure of how similar these two subsequences are. For example, if the two sequences are base pairs in the DNA strands, then we might consider them similar if they have a long subcommon subsequence. If the sequence X has M symbols and sequence Y has N symbols, then the sequence X and Y have 2 to the power of M and 2 to the power of N possible subsequences, respectively. Selecting all possible subsequences of X and Y and matching them could take a prohibitively long time unless M and N are very small. We shall see in Chapter 15 how to use a general technique known as dynamic programming to solve this problem more efficiently. We are given a mechanical design in terms of a library of parts, where each part may include instances of other parts, and we need to list the parts in order so that each part appears before any part that uses it. If the design comprises n parts, then there are n factorial possible orders, where n factorial denotes the factorial function. Because the factorial function grows faster than even an exponential function, we cannot feasibly generate each possible order and then verify that within that order each part appears before the parts using it, unless we have only a few parts. This problem is an instance of topological sorting, and we'll see an example in Chapter 22. And then more points here. We are given n points in the plane, and we wish to find the convex hole of these points. The convex hole is the smallest convex polygon containing the points. Intuitively, we can think of each point as being represented by a nail sticking out of a board. The convex hole would be represented by a tight rubber band that surrounds all the nails. Each nail around which the rubber band makes a turn is a vertex of the convex hole. Any of the 2 to the power of n subsets of the points might be the vertices of the convex hull. Knowing which points are the vertices of the convex hull is not quite enough either, since we also need to know the order in which they appear. There are many choices, therefore, for the vertices of the convex hull. Chapter 33 gives 2 good methods for finding the convex hull. These lists are far from exhaustive, as you have probably surmised from this book's heft. Exhibit 2 characteristics that are common to many interesting algorithm problems. They have many candidate solutions, the overwhelming majority of which do not solve the problem at hand. Finding one that does, or one that is the quote best, can present quite a challenge. 2, they have practical applications. Of the problems in the above list, finding the shortest path provides the easiest examples. A transportation firm, such as a trucking or railroad company, has a financial interest in finding the shortest paths through a road or railroad network because taking shorter paths result in lower fuel and labor costs. Or a routing node on the internet may need to find the shortest path through the network in order to route a message quickly. Or a person wishing to drive from New York to Boston may want driving directions from an appropriate website, or she may want to use her GPS while driving. Not every problem solved by algorithms has an easily identified set of candidate solutions. For example, suppose we are given a set of numerical values representing samples of a signal, and we want to compute the discrete Fourier transformation of these samples. The discrete Fourier transformation converts the time domain to the frequency domain, producing a set of numerical coefficients, so that we can determine the strength of various frequencies in the sampled signal. In addition to lying at the heart of signal processing, discrete Fourier transformations have applications in data compression and multiplying large polynomials and integers. Chapter 30 gives an efficient algorithm, the fast Fourier transformation, commonly called the FFT, for this problem, and chapter also sketches out the design of a hardware circuit to compute the FFT. Interesting. So we got a lot of stuff we're going to learn here. Data structures. This book also contains several data structures. A data structure is a way to store and organize data in order to facilitate access and modifications. No single data structure works well for all purposes, so it's important to know the strengths and limitations of several of them. Technique. Although you can use this book as a cookbook for algorithms, you may someday encounter a problem for which you cannot readily find a published algorithm. Many of the exercises and problems in this book, for example. This book will teach you the techniques of algorithms design and analysis so that you can develop algorithms on your own. Show that they give the correct answer and understand their efficiency. Different chapters address different aspects of algorithmic problem solving. Some chapters address specific problems such as finding medians and order statistics in Chapter 9, computing minimum spanning trees in Chapter 23, and determining a minimum flow or maximum flow in a network in Chapter 26. Other chapters address techniques such as divide and conquer in Chapter 4, dynamic programming in Chapter 15, and amortized analysis in Chapter 17. Hard problems. Most of this book is about efficient algorithms. Our usual measure of efficiency is speed, i.e., how long an algorithm takes to produce its result. There are some problems, however, for which no efficient solution is known. Chapter 34 studies an interesting subset of these problems, which are known as NP-complete. Why are NP-complete problems interesting? First, although no efficient algorithm for an NP-complete problem has ever been found, nobody has ever proven that an efficient algorithm for one cannot exist. In other words, no one knows whether or not efficient algorithms exist for NP-complete problems. Second, the set of NP-complete problems has the remarkable property that if an efficient algorithm exists for any one of them, then efficient algorithms exist for all of them. This relationship among the NP-complete problems makes the lack of efficient solutions all that more tantalizing. Third, several NP-complete problems are similar, but not identical to problems for which we do know the efficient algorithms. Computer scientists are intrigued by how a small change to the problem statement can cause a big change to the efficiency of the best known algorithm. You should know about NP-complete problems because some of them arise surprisingly often in real applications. If you are called upon to produce an efficient algorithm for an NP-complete problem, you are likely to spend a lot of time in a fruitless search. If you can show that the problem is NP-complete, you can instead spend your time developing an efficient algorithm that gives a good but not the best possible solution. As a concrete example, consider a delivery company with a central depot. Each day, it loads up each delivery truck at the depot and sends it around to deliver goods to several addresses, right? Like Amazon or something. At the end of the day, each truck must end up back at the depot so that it's ready to be loaded for the next day. To reduce costs, the company wants to select an order of delivery stops that yield the lowest overall distance traveled by each truck. This problem is well known the traveling salesman problem, and it is NP complete. It has no known efficient algorithm. Under certain assumptions, however, we know of efficient algorithms that give an overall distance which is not too far from the smallest possible, or too far above the smallest possible. Chapter 35 discusses such approximation algorithms. Parallelism. For many years, we could count on processor clock speeds increasing at a steady rate. Physical limitations present a fundamental roadblock to ever-increasing clock speeds. However, because power densities increases superlinearly with clock speed, chips run the risk of melting once their clock speeds become high enough. In order to perform more computations per second, therefore, chips are being designed to contain not just one, but several processing cores. We can liken these multi-core computers to several sequential computers on a single chip. In other words, they are a type of parallel computer. In order to elicit the best performance from multi-core computers, we need to design algorithms with parallelism in mind. Chapter 27 represents a model for multi-threaded algorithms which takes advantage of multiple cores. This model has advantages from a theoretical standpoint, and it forms a basis of several successful computer programs, including a championship chess program. Algorithms as a technology. Suppose computers were infinitely fast and computer memory was free. Would you have any reason to study algorithms? The answer is yes, if for no other reason than that you would still like to demonstrate that your solution method terminates and does so with the correct answer. If computers were infinitely fast, any correct method for solving a problem would do so. You would probably want your implementation to be within the bounds of good software engineering practice. For example, your implementation should be well designed and documented, but you would most often use whichever method was the easiest to implement. Of course, computers may be fast, but they are not infinitely fast, and memory may be inexpensive, but it's not free. Computing time is therefore a bounded resource, and so is space and memory. You should use these resources wisely, and algorithms that are efficient in terms of time or space will help you do so. Efficiency. Different algorithms devised to solve the same problem often differ dramatically in their efficiency. These differences can be much more significant than differences due to hardware and software. As an example, in Chapter 2, we will see two algorithms for sorting. The first is known as insertion sort, which takes time roughly equal to some constant times n squared to sort n items, where C1 is a constant that does not depend on n. The second merge sort takes time roughly equal to some constant n times the log of n, where the log of n stands for log base 2 of n, and C2 is another constant that also does not depend on n. Insertion sort typically has a smaller constant factor than merge sort, so that C1 is less than C2. We shall see that the constant factors can have far less of an impact on the running time than the dependence on the input size n. Let's write insertion sort running time as some constant C times n, and merge sort as running time of some constant C2 times n times the log of n. Then we see that where insertion sort has a factor of n in its running time, merge sort has a factor of log n, which is much smaller. For example, when n equals 1000, log n is approximately 10, and when n equals 1 million, log n is approximately only 20. Although insertion sort usually runs faster than merge sort for a small input size, once the input size n becomes large enough, merge sort advantage of log n versus n will more than compensate for the difference in constant factors, no matter how much smaller C1 is than C2. For a concrete example, let us pit a faster computer A running insertion sort against a slower computer B running merge sort. So we know that insertion sort takes quadratic time, whereas merge sort takes log time. So we know that the merge sort is a lot faster than insertion sort for large inputs. So if we have computer A that's running insertion sort and against a slower computer B that's running merge sort, they each must sort an array of 10 million numbers. So even though the computer B, which is slower, is running a faster algorithm here, I bet you it's going to do it faster. Although 10 million numbers might seem like a lot, the numbers are 8-byte integers. If the numbers are 8-byte integers, then the input occupies about 80 megabytes, which fits in the memory of even an inexpensive laptop computer many times over. Suppose that computer A executes 10 billion instructions per second, faster than any single sequential computer at the time of this writing, and computer B executes only 10 million instructions per second. 10 billion, okay, so then 10 million. So that the computer is 1,000 times faster than computer B. To make the difference even more dramatic, suppose that the world's craftiest programmer codes insertion sort in machine language for computer A, and the resulting code requires 2n² instructions to sort n numbers. Suppose further that an average programmer implements merge sort using high-level language with an inefficient compiler, with the resulting code taking 50 n log n instructions to sort 10 million million numbers. Computer A takes 2 times 10 to the power of 7 squared instructions divided by 10 to the power of 10 instructions per second, which is 20,000 seconds, more than 5.5 hours, while computer B takes less than 20 minutes. By using an algorithm whose running time grows more slowly, even with a poor compiler, computer B runs more than 17 times faster than computer A. The advantage of merge sort is even more pronounced when we sort 100 million numbers, where insertion sort takes more than 23 days. Merge sort takes under 4 hours. In general, as the problem increases, so does the relative advantage of merge sort. Algorithms and other techniques. The example above shows that we should consider algorithms like computer hardware as a technology. The total system performance depends on choosing efficient algorithms as much as on choosing fast hardware. Just as rapid advances are being made in other computer technologies, they're being made in algorithms as well. You might wonder whether algorithms are truly the important on contemporary computers in light of other advanced technologies such as advanced computer architectures and fabrication technologies, easy-to-use, intuitive graphical user interfaces, object-oriented systems, integrated web technologies, and fast networking, both wired and wireless. The answer is yes. Although some applications do not explicitly require algorithmic content at the application level, such as simple web-based applications, many do. For example, consider a web-based service that determines how to travel from one location to another. Its implementation will rely on a fast hardware, a graphical user interface, wide area networking, and also possibly object orientation. However, it would also require algorithms for certain operations such as finding routes, probably using the shortest path algorithm, rendering maps, and interpolating addresses. Moreover, even an application that does not require algorithmic content at the application level relies heavily upon algorithms. Does the application rely on fast hardware? The hardware design uses algorithms. Does the application rely on graphical user interfaces? The design of any GUI relies on algorithms. Does the application rely on networking? Routing in networks relies heavily on algorithms. Was the application written in a language other than machine code? Then it was processed by a compiler, interpreter, or assembler, all of which makes an extensive use of algorithms. Algorithms are at the core of most technologies used in contemporary computers. Furthermore, with the ever-increasing capacities of computers, we use them to solve larger problems than ever before. As we saw in the above comparison between insertion sort and merge sort, it is at a larger problem size that the differences in efficiency between algorithms become particularly prominent. Having a solid base of algorithmic knowledge and techniques is one characteristic that separates the truly skilled programmers from the novices. With modern computing technology, you can accomplish some tasks without knowing much about algorithms, but with a good background in algorithms, you can do much, much more. Nice. So I believe that is the end of chapter 1. Woo!